The word geomorphology derives from three Greek words, geo the earth, morph form, and logo discourse. Geomorphology is therefore a discourse on earth forms. The term was coined sometime in the 1870s and 1880s to describe the morphology of the Earth's surface, e.g. the Marguerite 1886 315, was originally defined as the genetic study of topographic forms, McGee, 1888 547, and was used in popular parlance. By 1896, despite the modern acquisition of its name, geomorphology is a venerable discipline. Box 1.1. Today, geomorphology is a study of Earth's physical land surface features, its landforms, rivers, hills, plains, beaches, sand, dunes, and myriad others. Some workers include submarine landforms within the scope of geomorphology, and some would add the landforms of other terrestrial-type planets and satellites in the solar system, Mars, the Moon, Venus, and so on. Landforms are conspicuous features of the Earth and occur everywhere. They range in size, from molehills to mountains to major tectonic plates, and their lifespans range from days to millennia to eons, figure 1.1. Geomorphology investigates landforms and the processes that fashion them. Form, process, and the interrelationships between them are central to understanding the origin and development of landforms. In geomorphology, form or morphology has three facets: constitution, chemical and physical properties described by material property variables, configuration, size, and form described by geometry variables, and mass flow, rates of flow described by such mass flow variables as discharge, precipitation rate, and evaporation rate, figure 1.2, Strahler 1980. These form variables contrast with dynamic variables, chemical and mechanical properties, representing the expenditure of energy and the doing of work associated with geomorphic processes. They include power, energy, flux, force, stress, and momentum. Take the case of a beach, figure 1.3. Constitutional properties include the degree of sorting of grains, mean diameter of grains, grain shape, and moisture content of the beach. Configurational properties include such measures of beach geometry as slope angle, beach profile, form, and water depth. Mass flow variables include rates of erosion, transport, and deposition. The nature of the mutual connection between Earth's surface process and Earth's surface form has lain at the heart of geomorphological discourse. The language in which geomorphologists have expressed these connections has altered with changing cultural, social, and scientific contexts. In very broad terms, a qualitative approach begun by classical thinkers and traceable through to the mid-20th century preceded a quantitative approach. Early writers pondered the origin of Earth's surface features, linking the forms they saw, such as mountains, to assumed processes such as catastrophic floods. An excellent example is the work of Nicholas Steno, alias Neil Steenson, 1638-86. While carrying out his duties as court physician to Grand Duke Ferdinand II at Florence, Steno explored the Tuscan landscape and devised a six-stage sequence of events to explain the current plains and hills. Steno 1916 ed. Figure 1.4. The first true geomorphologists such as William Morris Davis and Grove Carl Gilbert also tried to infer how the landforms they saw in the field were fashioned by geomorphic processes. Currently, there are at least 4 approaches used by geomorphologists in studying landforms. Slaymaker 2009. See also Baker and Twiddle 1991. 1. A process-response process form or functional approach that builds upon chemistry and physics and utilizes a systems methodology. 2. A landform evolution approach that has its roots in historical geological science, history, and that explores the important historical dimension of many landforms. 3. An approach that focuses on characterizing landforms and landform systems, and that stems from geographical spatial science. 4. An environmentally sensitive approach to landforms, forms, systems of landforms and landscapes at regional to global scales. This book will not look specifically at the third and fourth approaches, although it will mention them in passing. Interested readers should read the fascinating paper by Joseph Menard and Ian S. Evans, 2008, The Process and Historical Approaches Dominate Modern Geomorphology, Summerfield, 2005, with the former predominating, at least in Anglo-American and Japanese geomorphology. They have come to be called surface process geomorphology or simply process geomorphology and historical geomorphology, e.g. Chorley 1978, M. Belton, and Thorns 1979. Although the tag historical geomorphology is not commonly used, historical geomorphology tends to focus around histories or trajectories of landscape evolution and adopts a sequential, chronological view. Process geomorphology tends to focus around the mechanics of geomorphic processes and process-response relationships, how geomorphic systems respond to disturb answers. Largely, historical geomorphology and process geomorphology are complementary and go hand in hand, so that historical geomorphologists consider process in their explanations of landform evolution, while process geomorphologists may need to appreciate the history of the landforms they investigate. Nonetheless, either a process or an historical approach has tended to dominate the field at particular times. Process studies have enjoyed hegemony for some 3 or 4 decades, but sidelined historical studies are making a strong comeback. George Gaylord Simpson, 1963, an American paleontologist, captured the nature of historical and process approaches in his distinction between immanence, processes that may always occur under the right historical conditions, weathering, erosion, deposition, and so on, and configuration, the state or succession of states created by the interaction of immanent process with historical circumstances. The contrast is between a what happens approach, timeless knowledge, immanence, and a what happened approach, time-bound knowledge configuration. In simple terms, geomorphologists may study geomorphic systems in action today, but such studies are necessarily short-term, lasting for a few years or decades, and principally investigate immanent properties. Yet geomorphic systems have histories that go back centuries, millennia, or millions of years. Using the results of short-term studies to predict how geomorphic systems will change over long periods is difficult owing to environmental changes in the occurrence of singular events. Configuration in Simpson's parlance, such as bouts of uplift and the breakup of land masses. Stanley A. Shum, 1991. See also Shum and Lichty, 1965, tried to resolve this problem and in doing so established some links between process studies and historical studies. He argued that as the size and age of a landform increase, so present conditions can explain fewer of its properties, and geomorphologists must infer more about its past. Figure 1.5 summarizes his idea. Evidently, such small-scale landforms and processes as sediment, movement, and riverbed forms are explicable. With recent historical information, river channel morphology may have a considerable historical component, as when rivers flow on alluvial plain surfaces that events during the Pleistocene deter mind, explanations for large-scale landforms, such as structurally controlled drainage networks, and mountain ranges, require mainly historical information. A corollary of this idea is that the older and bigger a landform, the less accurate will be predictions and postdictions about it based upon present conditions. It also shows that an understanding of landforms requires a variable mix of process geomorphology and historical geomorphology, and that the two subjects should work together rather than stand in polar opposition. Such studies were difficult and largely educated guesswork. However, the brilliant successes of early historical geomorphologists should not be overlooked.